This conference will now be recorded.
Welcome everyone to another OCP TAP meeting. Actually, this is number 66. So today we have Professor Edward Lee presenting to us like one of his works. So Professor Edward Lee is the Robert S. Pepper Distinguished Professor in Electrical Engineering and Computer Science at the University of UC Berkeley, where he has been the faculty since 1986. He is the author of Plato and the Nerd, the creative partnership of human and technology, and a number of textbooks and research monographs, and more than 300 papers and technical reports. Lee has delivered more than 170 keynotes and presentations. I'm assuming 171 now, counting this one. Invited talk and at venues worldwide, and has graduated at least 35 PhD students. Professor Lee's research group studies cyber physical systems. I need to know about this term, actually, it's new to me, which integrates physical dynamics with software and network. His focus is on use of deterministic models as a central part of engineering toolkit for such systems. He is the director of 9 University Terra Swarm Research Center, the director of, how do you pronounce this? iCyPhy? I think I did good, right? Good. The Berkeley Industry Cyber Physical System Research Center, and director of Berkeley Ptolemy project. Okay. From 2005 to 2008, he served as a chair of the EE division and the chair of the EECS Department at UC Berkeley. He has led the development of several influential open source software packages, notably Ptolemy and its various spin-offs. He received his Bachelor of Science degree in 1979 from Yale University with a double major in computer science and engineering and applied science, as an SM degree in EECS from MIT in 1981, and a PhD in EECS from UC Berkeley in 1986. From 1979 to 1982, he was member of technical staff at Bell Labs in Holmdel, New Jersey, in Advanced Data Communication Laboratory. He is a co-founder of BDTI Inc., where he is currently a senior technical advisor and has consulted for a number of other companies. He is a fellow of IEEE, was an NSF Presidential Young Investigator, won the 1997 Frederick Emmons Terman Award for Engineering Education, and received the 2016 Outstanding Technical Achievement and Leadership Awards from IEEE Technical Committee on Real-Time Systems. So, wow. So with no further ado, Edward, I'll give the floor to you.
Thanks, Ahmad. I appreciate it. That bio is a little out of date. I'm not exactly sure where you found it, but it's mostly accurate. So the TerraSwarm project, however, has ended, fortunately. So I'm not dealing with that rather nightmarish management role. But in any case, I wanted to start by welcoming people to interrupt me and stop me. I really prefer that generally. You don't have to hold questions or comments until the end. I'm perfectly happy to be diverted at any time. This talk is actually very impromptu. I mean, I actually just met Ahmad for the first time yesterday, and he asked me to do this yesterday. I happen to have a talk that I actually gave. I've given it 3 times in the last few weeks, and so
perfect.
I have something ready that I think will be of interest to people who are working on distributed systems, and I guess a lot of people are particularly interested in how you can take advantage of synchronized clocks in distributed systems. So I'd like to try to address that. And it happens that this talk that I happen to have ready kind of addresses that. So let me share my screen, but then, again, encourage you to interrupt at any time. I guess you can do that by just turning on the audio. And
we have also a chat. So if you're more comfortable, guys, you can always use the chat as usual. And also, I want to thank Hisham for making the connections.
Great. So I want to emphasize that the work that I'm going to be talking about is pretty collaborative, and the particular technical contributions in this talk are there's several people who have contributed quite significantly to it, and those are listed here as co-authors. And I've labeled this as an impromptu talk because it was basically just organized yesterday. So, okay, so there's a couple of references. This is pretty new work, and so there's two papers in archive, one of which, the older one of which is actually almost, well, a little more than 2 years old actually, was kind of more aimed at the database community, which is really not my community. And we tried to get this published in database conferences, and there didn't seem to be a match. So it's been rejected twice by two major conferences. So, but the second one, which is much more recent, is aimed at my own community, which is really working in, as Ahmad mentioned, cyber physical systems. And these are systems where you have, the whole goal of the system is not just computation. So it's not just data processing, but it's also engaging some physical processes. So, think self-driving cars and that kind of thing. So the work is rooted in this very well-known statement from my colleague, Eric Brewer, who in a keynote that he gave at a major database conference in 2000, introduced what he called the CAP theorem. And it's a pretty obvious statement. In fact, it's, in some ways, it's almost an insult to mathematics to call it a theorem because it's really pretty obvious. But Eric, I think, made a really big contribution to the community by just articulating this and putting it really front and center. So the statement is really quite simple, which is that if you, in a database system, I think probably everyone here has at least an intuitive notion of what consistency means. It means basically that you would like, if you've got replicas of the database scattered around machines that might be scattered around the world, you would like some level of agreement on the value of a record across the entire database. So that agreement is what we call consistency. And availability is the ability that the database system has to respond to queries for those records. And Eric pointed out very simply that if you lose network connectivity, so in other words, you get a network partition, you're going to have to either give up consistency or you're going to have to give up availability. And it's really pretty obvious because if you have a record that is potentially getting updated in different machines, in different parts, different replicas of the database, if you lose network connectivity and you get a query for the value of a record, you can either not respond, in which case you sacrifice availability, or you can respond with the local data that you have, in which case you really have no assurance that that data is consistent with what any other replica of the database might have for that same record. So it's sort of an obvious statement, but me and my group, the people that we were working with on this, realized that it had applicability to a much broader class of systems. And so that's kind of what I'd like to reflect here and address. So let me just lay it out very clearly. If you have two software components, each of which have copies of some variable X, so there's a shared variable and they're connected through a network, then consistency is in some sense just intuitively agreement on the value of that shared variable. and availability is just your ability to respond to queries. Now, my interest is systems that are like this. They have computational components that are networked, but they also have as an integral part of their behavior some physical plant, like cars, intersections, roadways, factories, aircraft, etc. And here, availability is just about the time that it takes you to respond to a query about the value of this shared variable. So if you take a long time to respond, you're less available than if you respond immediately. So that's all pretty intuitive. So the first thing that I'd like to point out is that the choice of emphasizing consistency or availability is very application dependent. There's no way that you can really decide which to emphasize in an application independent way. So, for example, here is a ADAS system, which is an advanced driver assist system that was demonstrated by Denso in 2018. And the idea here is simply that it's a system that many cars today are equipped with. It's got a forward-looking camera. And if it spots a pedestrian, in this particular demo, there's a cardboard pedestrian standing in front of the car. If the camera spots a pedestrian, it's going to apply the brakes. And so the overall architecture of a system like this is you've got some braking system, which is what's going to actually actuate the brakes. And it has a number of inputs. And in this case, it's got inputs from the ADAS system, but also, of course, inputs from the brake pedal. And so this student at TU Dresden that I have been working with for a few years, Christian Menard, he implemented, well, first of all, he looked at an ADAS implementation using AutoSAR, which is a popular software framework that that many automotive companies are using, and he identified flaws in this system that were a consequence of non-determinism in the communication fabric. And then he re-implemented it using a software system that we've been working on collaboratively called Lingua Franca that really emphasizes deterministic interaction over networks. But he noticed something that in his implementation, that the mere existence of the ADAS system was causing delays in the processing of the brake pedal request. So we quickly realized that the system he had designed was emphasizing consistency over availability. The design was such that the system couldn't respond to an input from the brake pedal until it had reached agreement about the value of shared variables. And reaching that agreement meant waiting for the braking assistant to finish its processing of the images that were coming from the camera. And so we quickly realized that this was kind of unacceptable behavior, and that in this particular application, you really wanted to emphasize availability over consistency for this particular problem. You want to respond immediately to the brake pedal, even at the expense of responding to inconsistent information. So there's another self-driving car scenario. Well, I guess let me make it really clear what I mean by consistency here. So you can think of this as the camera takes a snapshot of the state of the world at some time t, and then the image analysis goes to work and gives you some result, which is information about the state of the world at time t. Of course, in physical time, it's going to take it a while to do that, right? But the information that it's giving you is about the state of the world at time t. So if you think of the brake pedal as giving you information about the state of the world at the time that the brake pedal gets pushed, which might be, say, epsilon larger than t, then if you're emphasizing consistency, the brake component has to wait for the result that gives the information about the state of the world at time t before it can respond to something that is telling it the state of the world at time t plus epsilon. And this is clearly the wrong thing to do in this case. Okay, so let me give another self-driving car scenario where the answer is opposite. This is also constructed in the same lingua franca framework, but this time by another student that I was working with at the time, Soroush Bateni, who was getting his Ph.D. at UT Dallas. And he built this system where you had vehicles communicating with a roadside unit wirelessly in order to gain access to a shared intersection. And so consistency in this case was agreement on the state of the intersection, and availability is the ability to enter the intersection. And in this case, Soroush observed that you wanted the opposite design criterion, which is that in the presence of network partitioning, you want to emphasize consistency over availability. You would rather have all of the cars stop and not enter the intersection than have the cars enter the intersection on the basis of inconsistent information about the state of the intersection, because the latter decision could yield accidents that would compromise safety. So the key thing is that you can't have your software framework decide for you whether consistency or availability is the more important criterion. It's very application dependent. So, okay, so let's drill in a little more detail. What do we mean by consistency, right? I mean, it seems like a very intuitive notion. It's agreement about the state of some distributed subsystem. But what do we mean by agreement, and what do we mean by state? There's sort of a very naive answer to this, which is that you could say, well, agreement is that at a particular physical time t, everyone agrees on the state of the value of a variable. But there is no such thing as that instant in time t in a distributed system. I mean, even with very well synchronized clocks, you don't really have a perfect notion of what a time t is, and you really would have to be, violating speed of light constraints anyway to get that kind of agreement. So consistency is a little more subtle, and we have to be careful to design it, to define it. And one of the things that I would like to point out is that actually, if you think of consistency as agreement on the state of a system, a state of a distributed system, fundamentally, there actually is no ground truth about the state of a distributed system. And consequently, you can't really define this in terms of the physical, ground truth, because there is no such ground truth. So, to prove this is really straightforward. Consider two state machines that are separated geographically. Maybe one of the state machines is in Singapore and one of them is in London. And the one on the left makes a transition from state A to state B, and the one on the right makes a transition from state C to state D. You can think of the overall system as transitioning from an initial state, which is the pair AC, to a final state, which is the pair BD. But how does it get there? Does it transition first through BC or first through AD? Or does it go directly with both transitions occurring simultaneously? Well, I mean, if you've studied relativity, you know that at a very fundamental level, there is no correct answer to this question. If these two transitions are occurring close enough in time, then the truth of which transitions were taken depends on your frame of reference. There's also a quantum mechanical interpretation that leads you to essentially the same answer, which is that you can't rely on the notion of a ground truth of the state of the system in order to define a semantic property like consistency. So how can we have agreement on something that's fundamentally ill-defined? So let me step back from the world of quantum mechanics and relativity to something much more practical. So think of a global banking system. And imagine that Joe's bank balance starts at $50 and a deposit occurs in London at 10 a.m. GMT where $100 gets added, okay? And a withdrawal occurs in Singapore at 10 a.m. plus 10 milliseconds, where you subtract $110. So the question now is, did an overdraft occur? In some sense, you would like the whole banking system to agree on whether an overdraft occurred. You don't want London to say yes and Singapore to say no. And so you'd like some agreement about what was the sequence of transitions that occurred in Joe's bank balance. So if you look at the numbers that I picked, well, at the speed of light, Singapore and London are 33 milliseconds apart, which means that even with perfect clock synchronization, two events that are 10 milliseconds apart are outside of each other's light cones, which means that the actual true order depends on your frame of reference. And you might say, okay, well, we're all in some inertial frame, but actually, you know, when you think about it, the systems that we're designing are doing things at nanosecond scales over distances of hundreds of kilometers on a spinning Earth with, you know, varying gravitational fields. If the order of events matters, you're not going to be able to establish a reliable ground truth on what the order of events is. So we're going to have to do better than that to get consistency, a notion of consistency here. Okay, so looking back at Joe's bank balance, well, you know, I mean, people build these systems. What do? Well, there's one very straightforward thing they can do, right? Which is in London, they timestamp the event using a local clock. That's all you can use to establish a timestamp. Okay, in Singapore, you timestamp the other event using another local clock. And now here comes the trick. Okay, you don't really care how well these clocks are synchronized. Well, you care somewhat. This overall system is better if there's some synchronization between these clocks. But from the perspective of the definition of the software, it becomes the semantics of the database that the order of transactions occurs in timestamp order. These timestamps are just numbers. Okay, so we now have a very well-defined notion of consistency because we can define exactly one correct behavior for this system. And the one correct behavior is that every observer should see the $100 deposit before the $110 withdrawal. And that's not because it physically occurred earlier. It's merely because these two numbers have an order. Okay, so this becomes a semantic property rather than some reflection of some ground truth in the physical world. So this is actually how, you know, many people build global databases. They use timestamps like this, and they define the order of events based on the order of the timestamps. If you think about this, you know, you sort of step back and look at what we're doing, we've created a logical notion of time that is really distinct from the physical notion of time. Once you've attached a timestamp to an event, okay, that timestamp becomes a logical property of that event, no longer a physical property. And all you have to do is build a software system that ensures that all observers see events in logical time order. Okay, I don't want to trivialize the implementation of that. It's not that easy to implement this, but we know how to do it. Anyone who's designed distributed software can do this. Okay, but you want to hire an expert. Okay, this is not something you want your 8th grader to do as a side exercise. But we know how to do this. We can make global systems that will process events in timestamp order. Of course, they do need network connectivity in order to ensure this. And I'm going to show you, in fact, that we can actually quantify the trade-off between consistency and availability, and we can relate it to the network latencies. Okay, one of the nice things that comes out of this notion of logical time is that we get a very clean notion of simultaneous events. Two events are simultaneous if they have the numerically identical timestamp, period. It doesn't matter. The physical notion of simultaneity becomes irrelevant. If they have the same timestamp, they get assigned the same timestamp when they enter the system, they are logically simultaneous. And then, of course, it becomes a business decision how you handle a simultaneous deposit and withdrawal. Do you charge for overdraft or don't you? That's a business decision now, not a technical decision. Okay, so the shared variables are just distributed views of the same quantity. And when one of them gets updated, for example, by reading a sensor or by having a deposit occur at an ATM, then you update the value of that variable, but you timestamp that update using a local clock. And then you send to the other components in your system your time-stamped update, okay? And I'm going to show you in a minute that it can be quite useful to manipulate that timestamp. So you might actually want, in the process of transporting it to another software component, you might want to reassign a larger timestamp. And the reason for doing that is actually to give up a measured amount of consistency in order to get better availability. I'll show you how that works in a minute. But for the moment, you can think of it as just, well, if we want perfect consistency, then we don't manipulate the timestamp. We just, when we update a variable locally, we timestamp that update event and broadcast to all the other components that timestamped event. So once we have this idea that the update has a timestamp, the update at the originating source has a timestamp, the update at the receiving end has a timestamp, we can now give a quantitative value to inconsistency. Okay, so we define the inconsistency from node J to node I to be the maximum over all the updates on J that are sent to I. The theory that I'm going to give you is all about worst case behavior of complete traces. Okay, that's what this theory talks about. So it's a maximum over all updates on J that are sent to I of the difference between these two timestamps. So if you insist that the timestamps be the same, then you're going to get what we call strong consistency, which is that you're going to require, in fact, that these timestamps be the same, which means the inconsistency should be 0. But I'll show you that it can be quite valuable to allow non-zero inconsistency because you can use it to improve the performance of your system. So strong consistency is all nodes will end up agreeing on the value of any variable at any logical time t. You do have to have a policy for handling simultaneous updates. And in the case of the bank balance, it's actually straightforward because if you're just adding numbers, the addition of numbers is associative and commutative, so you can just use that property to have an unambiguous handling of simultaneous updates. But in other more general cases, you might not have that, so you might need to prioritize certain nodes, for example. But in any case, you will have to specify in your program your logic associated with handling simultaneous events. Okay, so if we use the logical time, this logical time notion in this car braking example, the camera timestamps a frame using a local clock. The braking assistant is a logically instantaneous operation because it's going to tell us, it's going to give us information about the state of the world at the same time. So we think of it as logically instantaneous, even if it takes physical time to do the computation. And consequently, the braking assistant sends to the braking system a time-stamped event where the timestamp reflects the local clock reading when the camera took the frame. So the brake pedal does something similar. When the driver presses the brake pedal, a timestamp is assigned using a local clock. And now the order of events is determined by the numerical relationship between those timestamps. And if we require strong consistency, we simply require the braking assistant to see these events in timestamp order. And this is what leads to the loss of availability that Christian complained about in this implementation that he built, okay? And that loss of availability is a direct result of the insistence on strong consistency. So strong consistency reduces availability. Okay, we can quantify availability equally easily. In fact, it's sort of more convenient to quantify unavailability. So the unavailability at node I, we can define as the maximum over all accesses of a shared variable at I, okay, of a difference between two numbers. But now those two numbers, one is a logical time and the other one is a physical time, okay? The physical time is the time at which the access to the updated shared variable is allowed. And you subtract from that the timestamp, and you get a measure of your unavailability. How long does it take in physical time for you to be able to deliver the agreed upon value of a variable? Okay, it's a direct measure of that. And I notice this is a completely measurable quantity because it's the unavailability at node I depends on the physical time at node I. So it's using a local clock, not the remote clock. It's comparing a local clock against a timestamp, which is a logical property. The fact that that timestamp was derived from a remote clock has become irrelevant. Once it became a logical time, that was no longer a pertinent issue. Okay, now it's also useful to have a constraint that unavailability be greater than or equal to 0, in which case you can define perfect availability as the unavailability is 0. There are circumstances, by the way, where you actually might even allow this unavailability to go negative, but it would take a little bit of an aside to explain why that is, but you can probably guess that that's going to come about because of clock synchronization errors. Nevertheless, let's just put that aside for the moment. And in practical systems, it's often useful to just constrain it to be greater than or equal to 0. So there's a third number that we need to define. So remember that I said we need to hire an expert to build the software system that ensures that all observers see events in timestamp order, okay? That's going to be someone who really knows how to design distributed software. In the process of making the system behave that way, this programmer is going to introduce time delays. We call those time delays processing offsets, okay? And there's a lot of detail in where these processing offsets come from, but it doesn't really matter that much for the purposes of this discussion. The fact is that they're just needed to make sure that things are processed in timestamp order, okay? So we define this processing offset similarly as a maximum between a physical time and a logical time, but which is very much like the unavailability. It looks like unavailability, except that it's for write events, all right? So in other words, let me try to make this clear. Unavailability is a physical time lag to read an agreed upon value of a state variable. The processing offset is a delay in physical time to updating the value of that variable, okay? And the reason that you need to delay the update of that variable is in order to ensure that the updates all occur in timestamp order, okay? So it's very similar to unavailability, but it's for write events. Now, this is going to be the last definition, and it's the fourth quantity involved in this overall result, which is something that we call the apparent latency, okay? And in my view, the use of apparent latency here is one of the more beautiful parts of this theory. I want to emphasize, we don't know what the network latency is from Singapore to London. In fact, you can't measure that. It's impossible to measure that. You can measure round trip latencies, but you can't measure one-way latencies, okay? Apparent latency is perfectly measurable. So the apparent latency for communication from node J to node I is simply the maximum over all messages from J to I of, again, a difference between two times, one a physical time and one a logical time. The logical time is the time of the original update at node J, and then the physical time of the received message at node I, okay? When the update occurs at node I, that occurs at a physical time, and when the update is received at node I, that occurs at a physical time according to node I's clock, all right, the local clock. And all you have to do to get this apparent latency is compare that against a timestamp that comes in on the message. So it's easily measured. Now, if your clocks are poorly synchronized, this apparent latency can even be negative. There's no constraint that it be greater than or equal to 0. It's simply the apparent, it's what seems to be the latency, okay? You get the message at time I, it's reflecting a value that was sent at time J at some other time, but that was on with respect to another clock, okay? So, but easy to measure. So we call this the apparent latency. And you can think of the apparent latency as consisting of actually 4 components. It consists of the processing offset, that's part of it, at the sending node, okay? The processing offset at the receiving node is not taken into account in this offset. The execution time overhead on the path from J to I, whatever software is involved in sending the message, the network latency from J to I, and the clock synchronization error. And I'd like to point out that these latter 3 quantities are extremely difficult to measure. In fact, the latter 2 quantities are impossible to perfectly measure, but the sum is trivially easy to measure. So we can put together these 4 quantities that I've defined and write down what we call the CAL theorem. And this is it's a quantification of the CAP theorem. So it relates consistency, availability, and network latency, not just network partitioning, but network latency, but it's actually apparent latency. So it's a measurable quantity that we can relate to consistency and availability. So the theorem says that the unavailability is simply the maximum of the processing offset at the same node, or the maximum over all sending nodes that send messages to I of the apparent latency from J to I minus your tolerance for inconsistency. Okay, so this is why we sometimes want to allow the inconsistency to get greater than 0, is because then it can compensate for latency in the network to reduce unavailability. Okay, so in words, unavailability is simply the larger of the local processing offset needed to ensure that timestamps are processed in order, or the apparent latency minus the tolerance for inconsistency. So if you increase your tolerance for inconsistency, you can improve your availability. It's an immediate consequence. This theorem has a very beautiful algebraic formulation in an alternative algebra called a max plus algebra, where you build a matrix. This gamma matrix contains your apparent latencies between any pair of nodes. So you can easily accommodate a very heterogeneous networks. For example, you might have 2 nodes that are on the same rack in a data center, and so their apparent latency from one to the other is quite small. The clock synchronization error is quite small. But you have those 2 nodes are in London, and you're communicating with a node in Singapore, and the latency between those nodes is much larger. Well, this matrix is represents all the point-to-point apparent latencies, and so it can represent very heterogeneous networks. And then you get a vector of unavailabilities at each of the nodes, which turns out to equal simply a matrix times a column vector with processing offsets. So you actually get a linear equation in this max plus algebra, which is really, in my view, quite a beautiful piece of mathematics to come out of this. So I'd like to somewhat switch gears now and say, how can we use this in practice, right? Because it's kind of a nice theory that says, well, okay, we can trade off consistency and quantify it. So we can design a system where we say, I'm willing to tolerate 100 milliseconds of inconsistency. The components can disagree for 100 milliseconds. And in exchange for that, how much do I improve my availability? Well, you can use this theorem to actually derive those numbers as a function of how you expect your network to behave. So we've been working on this programming framework called lingua franca, which is, it's a polyglot coordination language. So it coordinates chunks of code that you write in standard programming languages. The ones that are currently supported by the software are C, C++, Rust, Python, and TypeScript. And those, it's a pretty broad set of languages used in very different contexts. And the emphasis of the coordination language is really on deterministic interaction between concurrent and distributed components. And so lingua franca automatically takes care of for you the processing of events in timestamp order. That's just built into the framework. You get that for free. And we have discovered that you can, because of that, you can use it to explicitly design systems that trade off consistency, availability, and network latency. So the way that a lingua franca, way a program looks is that you have these reactions to events that are specified in the target language. So in this particular example shown on the screen, this reaction is written in C, and it just does a couple of printfs in this case. And then you compose your components using a syntax that essentially then, well, the syntax is textual, but we have this wonderful tool that was developed by our colleagues at Yale University, north of Germany, that automatically generates a diagram from the program. So it's very easy to visualize the structure of your program. And in fact, all the diagrams that I've shown of the ADAS system and the four-way intersection example, those are actually diagrams automatically generated from lingua franca programs by this interactive visualization. So the braking system looks like this, but now notice a trick you can play. Okay, in lingua franca, when I connect the vision system to the braking system, I can explicitly manipulate the timestamp. So what this particular line of code says is that the output events from the vision system will become inputs to the braking system, but 10 milliseconds later in logical time. So the timestamp gets incremented by 10 milliseconds. So one line change to the original lingua franca program that Christian Menard had created, and all of a sudden the unavailability that he observed vanishes. Okay, because as long as the vision system, the actual physical time that it takes to do its stuff, to analyze that camera frame, is less than 10 milliseconds, because we're introducing a small tolerance for inconsistency here, we get the ability to get perfect availability. We can respond immediately to brake pedal signals without compromising the fact that we're processing events in timestamp order. So this is the thing that I like the most, is this ability to be able to really play off tolerance for inconsistency against the availability that you need. So it does, in this case, require that the apparent latency of the path from the camera to the braking system will have to be less than 10 milliseconds in order for this system to be able to immediately respond to the brake pedal. Okay, the apparent latency. So that says something. If you end up implementing the vision system on a separate processor, you're going to have to synchronize the clocks and ensure that the sum of the clock synchronization error, the network latency, and the computation times don't exceed 10 milliseconds. Okay, that's the design criterion that you can derive now from the Cal theorem on the basis of this specification for the program's requirements for consistency. You can also specify your requirements for availability in the program. And we do these in lingua franca by specifying what we call deadlines. And so in particular, the response to the brake pedal, we've associated with that a 3 millisecond deadline. And what we mean by that is that an event that is timestamped here with some timestamp t needs to be handled in physical time no later than t plus 3 milliseconds. Okay, so this tolerance for 3 milliseconds adds to our 10 milliseconds here, and we get an overall requirement now of we need the sum of the network latency, computation times, and clock synchronization error to not exceed 13 milliseconds. We've expressed a tolerance of 3 milliseconds for unavailability, a tolerance of 10 milliseconds for inconsistency, and we can derive from that the requirements on the network. And in the max plus algebra, in this case, we just have two components, so we get a 2x2 matrix, and we can solve the equations in closed form for this particular example, and we can derive that 13 millisecond requirement on network latencies from this program specification. Okay, this sort of walks through that derivation, but I don't need to bore you with the details. You can take my word for it, I think. So there's potentially still a problem, right? We've got this system now that if the network actually delivers and our clock synchronization is working well enough, then everything will behave beautifully. We'll meet the deadline at the braking system. But what if the network breaks? Or our clock synchronization algorithm comes under attack and starts to drift and eventually gets far enough out that we can no longer guarantee that 13 milliseconds of apparent latency, right? This can always happen. Murphy's law is going to hit you. No matter what system you design, something can always break. So the Cal theorem tells you that you have a choice now. You have to further give up one of availability or consistency. You cannot avoid it. It's absolutely unavoidable. You have to either sacrifice availability beyond the 3 milliseconds, missing the deadline, or you have to sacrifice consistency beyond your 10 milliseconds, in which case you won't be processing events in timestamp order. Okay? You're forced to make this choice. So it turns out that we realized that we had implementations of the lingua franca system that give us this choice. Okay, we had built, this was mostly the work of Soroush Bateni, which most of it he did while he was doing his Ph.D. at Dallas, and I then hired him as a postdoc where he worked further on it. But he had built these two coordination mechanisms for distributed execution of lingua franca programs. The centralized coordinator is very conservative, and it absolutely guarantees that every component processes events in timestamp order, which means that it guarantees the consistency requirements that you've specified in your program will be maintained at the expense of availability. If you lose network connectivity, this particular coordination mechanism will stop progress in the components. So you sacrifice availability. But he also built a decentralized coordinator that will sacrifice consistency if the network breaks. And this turns out it extends methods that are used commonly in distributed databases. So for example, Google Spanner uses this technique. We had published a paper using this technique several years earlier, and we called it TIDES. And this technique requires clock synchronization. But the way the decentralized coordinator works is that in order to process events in timestamp order, each component in the system just watches its local clock. And when its local clock hits a pre-calculated threshold, it proceeds and assumes that it's seen all the inputs that have timestamps less than some value. Okay? And that technique has the very nice feature that if your network goes out of spec and stops behaving the way you expect, every component continues nevertheless to process events locally at the expense of consistency. It no longer can assure consistency, but it will guarantee availability. So as a consequence, you can guarantee that all your deadlines get met at the expense of consistency. So in the case of the ADAS system, what we want to do is, in fact, use the decentralized coordinator, because you want the braking system to always maintain availability regardless of what the network is doing. Now, it turns out you can also, in lingua franca, with a one-line change in the program, sacrifice consistency altogether and just say, well, I don't know if 10 milliseconds is enough. I'm just gonna just throw consistency out the window. And so what we call this a physical connection between components. And what it does effectively is at the sending end, it just discards the timestamp. And at the receiving end, it reassigns a new timestamp based on the local physical clock. And so in effect, this design says, I'm willing to tolerate unbounded inconsistency in exchange for totally predictable availability. A price that you pay for this is now the system also becomes non-deterministic. In this simple example, that non-determinism doesn't matter that much. So this might actually be a reasonable design for a really simple system like this. But in bigger, more complicated systems, introducing non-determinism into the program has a big price, which is that you basically lose testability. Once you have a non-deterministic program, you can't really use regression tests anymore because there's no known good behavior for the system. And so we kind of discourage people from doing this. If you can accomplish your goals instead by specifying a tolerance for inconsistency, keeping determinism, you get deterministic behavior when the network is behaving according to spec. When the network falls out of spec, what you want is to be able to detect that situation and to handle it as a fault condition. And so that's the kind of design style that we favor. So I started with this sort of banking example, and here's a very simple implementation in lingua franca of exactly that banking example. This is the world's smallest database. It stores one person's bank balance. That's all it stores. And it has some number of replicas of them, which get rendered, that gets constructed in lingua franca like this line right here, where specify an array of replicas according to a parameter, which defaults to 4 replicas in this case. You connect up this bank of replicas, and you have a bunch of, say, ATM machines, right? These are gathering user input. This little diamond with a P in it is the lingua franca notation that's rendered in the diagrams like this for what we call a physical action, which generates events using the local clock to timestamp them. Okay, so what happens is user inputs get timestamped with a local clock at any of in this case 4 locations, but you can parameterize that. Each update gets broadcast to all the replicas. The replicas respond to queries about the bank balance, and you can use the Cal theorem to derive your delays here as a function of your apparent latencies. And interestingly enough, because this is a feedback system, the clock synchronization errors will cancel out, okay? Because eventually you're interested in the response time back to the same component. So it really doesn't matter how far off the clocks are at the replicas over here, because they cancel out in that loop. Of course, they don't cancel out relative to the user inputs, so they still have an effect. If you use centralized coordination on this, then the program will enforce strong consistency. And if your network breaks, the program will stop responding to user inputs. It can't respond consistently, so it just stops responding. So the Cal theorem tells us that, you know, the price we pay for the strong consistency is unavailability, and you can derive what that unavailability will be, and then, you know, ascertain whether that is the appropriate design for your system. If the network becomes totally partitioned, you completely lose network connectivity, then consistent with the CAP theorem, then unavailability becomes unbounded. So if you use decentralized coordination, on the other hand, you can enforce high availability, meaning that you will always respond to a user within some bounded amount of time, but you may do so at the expense of inconsistency. So again, I want to emphasize that, you know, if you're designing a banking system, which of these 2 approaches to take is a business decision. It's not a technical decision. You need to decide whether, you know, if your network breaks, are you going to really annoy the customers by not delivering cash at the ATM machines, or are you going to deliver cash on the basis of the best information that you have currently? That's a business decision and not a technical decision. So the Cal theorem still tells us exactly what to expect in terms of consistency and availability, and what happens when the network gets partitioned. So in summary, CAP theorem, network partitioning means you have to sacrifice consistency or availability. Cal theorem quantifies all of this and gives you a rather beautiful numerical relationship that involves apparent latency, which is a measurable quantity, in relation to availability and consistency. Centralized coordination preserves consistency for all network latencies at a cost in availability. Decentralized coordination preserves availability for all network latencies at a cost in consistency. We know we have to sacrifice one or the other if network latencies get too high. In both cases, if you lose availability or consistency, this shows up in the program as explicit fault conditions. So in lingua franca, when you specify a deadline, which is a requirement on availability, you can also specify a fault handler, a piece of code to get invoked when that deadline gets violated. So a much shorter summary is agreement takes time. Agreement is consistency, and that takes time is availability. And so that's really the short story. But the fact that we can systematize this, turn it into an engineering principle where you can really design your system to fine tune these quantities and to build in your business decisions as an assumption on your network. You can also derive your requirements on the network. You know, I mean, I talk to many people who work on clock synchronization, and they say, well, better clock synchronization is always better. Well, not necessarily. If you have network latencies that are 30 milliseconds, it doesn't really help to get your clock synchronization down to nanosecond scale, because your network latency is going to dominate over the clock synchronization. So these are the papers, and I'd be happy to take any questions or comments from anyone.
Thank you very much. So let's open the floor for questions. Nobu, go ahead.
Yeah, thank you. Well, thanks a lot for giving great overview about logical clock. I always wanted to learn about logical clock, and I didn't have people to ask questions. And actually, you already sort of answered in your very last part of your talk that improving the clock synchronization doesn't always help. But in which case, but I had been hoping that we could somehow help to reduce the effort of attribution in this sort of logical clock business. And my question is there any way that clock synchronization helps in, say, particularly distributed system?
Yeah, well, I'm very interested myself in cyber physical systems, which often have very tight deadline constraints, and you know, they also have requirements for networks with very predictable latencies, right? And often, you know, in factory automation or on cars or on airplanes, they use specialized networks in order to get very predictable latencies. And in those contexts, having very precise clock synchronization is hugely valuable, because otherwise, you know, the clock synchronization error does end up increasing latencies, and latencies are not good in feedback control systems. Right.
So again, I mean, now I understand more, and that the network latency can easily become a bottleneck, and so at first glance, it doesn't do much better if you improve the synchronization much better than network latency. It's sort of at the moment bottom line, is it?
Yeah. So one way to think about it is that in the theory that we've developed, network latency and clock synchronization error always appear summed. You add the two together. They never appear independently. It's always the sum of the two, right? And so if one is really small and the other is really large, then the small one doesn't matter, right? So in some sense, there's sort of a cost optimization that you could do also, where, you know, you have to spend a certain amount on your network and you have to spend a certain amount on your clock synchronization. What you want to optimize is the sum of those two quantities, not the individual quantities.
I see, thank you.
I have a question.
Go ahead, Hisham.
Yeah, thanks, Professor Edward. It's excellent presentation as usual. But
yeah,
based on everything you described today and before, is there any meaning for something like this packet should arrive at that destination on that time, like on time packet delivery, or on time, certain events happen on time, on a given time? Any meaning for this?
Yeah, in fact,
any way to guarantee it or any way to make it happen?
So the deadlines in lingua franca are specifications of that type. They say that they specify a requirement that an event with timestamp T should be seen at a physical time that is no bigger than T plus some deadline. Okay, and that's a requirement. Part of what this theory tells you is that you actually cannot guarantee that that requirement will be met unless you can guarantee your network latency, right? So, but you know, another way to think about it is that any engineered system, absolutely any system, will behave correctly only under some assumptions, right? If you know you submerge your electronics in salt water, or you know hit it with a blowtorch, it's not going to behave the way it was spec'd, right? So every system that you design behaves correctly only under some assumptions. One of the nice things about this theory is that you can make very explicit what your assumptions are about your network behavior. You can tie it directly to your design, right? You have your design requirements, and from the design requirements, you can derive your network requirements.
Yeah, good point. Thank you very much.
Yeah.
Maybe a follow-up on these questions. Let's say basically the latency determining where you're gonna get, basically, if you go further, you get diminishing returns, basically on the clock synchronization. That applies to, I want to see where is that applying? That applies on distributed systems in general, or it applies to, let's say, when you have something that needs partition tolerance, let's say a database. Because let's say when you have, for example, what Hisham was bringing up as an example, basically a packet when it arrives, or you want to, let's say, optimize, let's say, certain pathways going through a network. Is that also considered a distributed system, or that's a different class, perhaps, of problems?
Yeah,
or
actually,
the last thing is how much is the latency important, and how much is the consistency of the latency important? So,
yeah, actually, one of the things that interests me is that some of the systems that we've been applying this to are not actually distributed systems at all. And if you remember, this apparent latency actually had 3 unmeasurable quantities: execution time, network latency, and clock synchronization error. Right? If you have a system that's not distributed, your clock synchronization error goes to 0. Your network latency becomes negligible. It's just, time to access shared memory, maybe. So what dominates? Execution time. But execution time now factors into the system design in the same way as network latency. It also results in a compromise between consistency and availability. And so, if you are running some really expensive, machine learning algorithm where, with affordable hardware, it's going to take you 3 seconds to do inference, that 3 seconds of computation time is going to cost you. It will cost you either in consistency or availability. You get to choose where you want to pay the price, but you're going to have to pay the price one way or the other. So this applies very broadly. It's sort of easiest to explain, I think, for distributed systems, but it also applies to just, ordinary systems.
Any more questions?
Yeah, I guess maybe I could ask one.
Yeah, go ahead.
Yeah, I don't know. Maybe it's too complicated for the whole thing, but yeah, we make sort of a system where individual devices takes time from different clocks, okay? But then we also allow the clients to compare the time they have with each other, okay? In a peer-to-peer fashion. But then on top of that, we've built something called latency path analysis, where you can define a path between nodes, and then we know what is the latency of that path, right? And so here you can apply some business logic. What do you think about that? Do you think that's useful? Does it apply to anything you've talked about here this evening?
I think it does. I think that ultimately a key part of what this whole theory gives you is an ability to kind of relate your business logic to your technical decisions. And I think that all too often this gets done in a very kind of ad hoc, intuitive way, I think. I think, you mentioned, for example, that you have the clients are comparing things. There's side channel information, right? And so if you try to run a chat board, for example, and your clocks are way off, right? People are going to see messages in very random orders that are going to be quite unexpected, and they're going to get annoyed with you, right? So, you know, these things, you can, I guess the point here is that you can kind of turn this into a much more of a engineering optimization than just an ad hoc intuitive feel that, well, just we got to make it better. You know, we need better clock synchronization, right? Or we need faster networks, you know, and just over provision is the answer. Well, no, you don't necessarily have to over provision. You can do the calculation, do the optimization, work the trade-offs using this theory.
Because initially we did the system so that we could discover essentially asymmetries where you know, you had large WAN distances. Okay, this is why we did it. So we looked at the unidirectional latency of these paths, so that if in one way, you know, across the Atlantic, you take one path and the other way you take another. Okay, we'd be able to see that. But maybe what we should do now is, you know, add the uncertainty to the latency and make it available on the individual machines as an API for applications running that. This is what I was thinking.
Yeah, I think that would be incredibly useful. I mean, one of the things that has frustrated me is that there's a lot of very sophisticated work in clock synchronization, very little in the way of standardized APIs, right? Where's the standard C library to, you know, be able to work with these synchronized clocks? It tends to be, you know, a little bit too vendor dependent and non-portable, the code that you build.
It's actually a work stream in OCP TAP, like an API which along with a timestamp gives you uncertainty, and Jochi Chalakov has done a lot of work on that. So yeah, I guess we're generally interested in it. And yeah, thank you very much. Thank you.
Yeah, one of the things we've been using lingua franca for is actually kind of measuring the actual behavior in distributed systems, right? We can get some very precise measurements using this system, and just because we have timestamps flowing everywhere. So
perhaps some question or contribution from me. Isn't TSN trying to somehow address this thing? For example, the time-sensitive networking is essentially trying to remove availability once consistency is not the case any longer. For instance, in a network, if the latencies are very high for so-called predefined high stream traffic, then if the latency is more than a certain boundary, then it actually removes that node as not available by not considering as consistent because it's too late, not meeting the demands. So for instance, if device latencies between synchronized nodes is very high, then it basically removes it as unsynchronized. In this fashion, the communication, which is crucial in this time-sensitive networking context, high traffic is actually stopped. Isn't this just addressed with this way, or?
yeah, I'm glad you brought up TSN, because actually I meant to mention it because it does give us a whole bunch of more knobs to turn in the design of the system. You know, but it's important to realize, you know, TSN is actually not one standard, it's actually a collection of standards. And there's a bunch of different features that it provides, and they have different utility. I mean, one of them, you know, the core of TSN is the clock synchronization. You know, I think that's probably the most important part of it. I don't know if everyone agrees with that statement, but I certainly feel that way. But some of the other ones are the methods that are provided in TSN to get bounded latency, right? One of them, very simply, is flow control, right? You prevent buffer overflows with flow control, and you can regulate buffer delays in your network through flow control. And you know that gives you the ability to actually come up with reasonably hard boundaries on network latencies. And if you have hard boundaries on network latencies, then you can use this decentralized style of control with very high reliability. So this is what Google Spanner does, for example. If you're familiar with Google Spanner, I don't think they use TSN, but they use dedicated trunks between their data centers that are flow controlled so that they don't get buffer overflows and TCP/IP retransmissions, which end up hugely, giving you a really long tail on your latencies, right? If you can truncate the tail on the latencies, then you can use this decentralized style of control and get very deterministic behavior from a distributed system with really quite high reliability. I think TSN is really, to me, it's been incredibly frustrating how slow it's been in sort of getting into deployed systems. It's maybe you guys know about stuff that I don't know about, but it seems like it's been frustratingly slow.
I mean, there are a lot of reasons. I can speak on that. Like, there were a lot of reasons from starting like the time server all the way down to like what it takes, like transparent clocks, boundary clocks, the scale, the servo. All of these things were problems, and this was the main objective for this project, time appliances project. And I will say, I'm glad, like, a lot of things changed, like this last 2-3 years, and we have a lot of solutions now. So we have like the time servers like completely like democratized now. Like we have like with a time card, and then like you have everything, like whole stack is open source. The switches, the hardware, like again, all the vendors did great. Like we got like a lot of things. We actually initially we were thinking in like boundary clocks and transparent clocks, like I don't know, there were two solutions or something. But then as we went further, we came to this conclusion that using transparent clocks is probably a better solution, although it looks like a little bit bad, let's say, for the scalability. But then in a lot of applications, again, there's no like clear cut or like a silver bullet for that. But the thing is, like, for our applications, it looked like better to have a transparent clock, because now you can have from every node multiple, let's say, readouts or things like that, all kinds of things. So like, you know exactly what's happening in the chain all the way up. Like you're not just measuring things to, let's say, the immediate boundary clock above you. And also on the hardware for the nodes and this, like the servos, for example, like here we have Lasse, he has an entire company like just like focusing on the servo basically. And I mean, all the vendors, we've got different vendors working. It's been a lot of like progress and a lot of fun, I will say, for us. Like, I mean, this is like my personal passion.
Good. I'm going to follow up with you offline on this, because I'd like to know which are these open source APIs, because stuff that we've been working with is all proprietary.
No, nothing proprietary. Everything we work on in this project is 100% open source. Like, as a matter of fact, like time card, everything's open source, including the design files, everything. Like, and then we have proofs, like someone I have no connection with, basically just took the design files and like executed on it and built it, and it works. You know, like unlike some other projects that they claim it's open source, but then you get a bunch of PDF files. Okay, how can I manufacture anything with it? Well, you can't. So it's just there for the open source. No, this is really open source, you know.
Cool. I'm going to follow up with you on that. So,
sure.
Yeah.
Any more questions? Okay, hearing none. Thank you very much again, Professor Lee. So looking forward working with you in the future. And we have this calls again bi-weekly. And see everyone in 2 weeks. Bye, everyone.
Great. Bye, everybody.
Thanks.
Thank you.